So first of all, I would like to thank you for accepting the invitation to give this seminar. So thank you, Graham. It's a real pleasure that you're finally here. Thank you all of you for being here. I'm just gonna brief interact a little bit, Graham, although I know that most of you already know him, but Graham was a student in the University of Oxford. He made his PhD there, and then he moved to Heidelberg University for 9 years. For 9 years working with big Heidelberg connection, then said about and all the big names there. Then he was back in England in the King's College, and then he moved to Birmingham, where I had the pleasure to work with him. Although we have known each other for very long before. Anyway, then he moved to finally to the University College, where he is a full professor there. He's been devoted his research since the postdoc probably to the development of algorithms for quantum dynamics calculations, and this is what he's going to talk about today. So thank you again.
Oh, thank you, Chris. Yeah, and yeah, it's really nice to be here. So Christina told me that this is so it's a sort of general lecture for good. It's something.
I don't know what you've done. Wait.
Computers. No,
Try again, just in case.
Nothing broken.
Nothing works anymore.
This is not working.
Okay, wait a second.
This is connecting. Yeah.
Wait. Because probably otherwise we use that one. So wait. The program is already running.
Aquí hay, ese es el puerto de sí.
No, es este aquí.
¿Lo cambiamos? Cambiamos.
Okay.
Prueba otra vez. Okay.
Sorry.
So what I did, sorry.
You probably do.
Yeah, Chris told me this is sort of a talk for the graduate school, so it's a bit of a general talk. I'm not going to really go into the detail of what I do, but I will obviously show some of the ideas and what it is that we're really trying to do in sort of a broad sense. Yeah? So the idea is what I'm going to cover. You say, it's interesting to control. Okay, so this is that. You can see from the title, really, what are we trying to do? We're trying to understand fundamental chemical reactivity, and there's a whole range of things in principle that we can do. As Chris mentioned, the thing we're trying to develop, what we call quantum dynamic simulations, and how we can apply them, and what sort of information can we get out of it. You know? So I was going to just to say a bit of background. What are we trying to do? And the whole field really comes from looking at molecular collisions, scattering experiments. And then more recently, and this is obviously where our interest comes in, you know, in the field of sort of photoactivated reaction dynamics, it's femtochemistry, getting down to atochemistry. Well, I'm not going to talk much about at all about that field, and then really how we try and do this. Okay, so this is a sort of general thing. Reaction dynamics. What is reaction dynamics? Now, when you study physical chemistry, you necessarily come across what is reaction dynamics, and well, you know, these are the different ways that we're trying to describe a reaction. Okay, so thermodynamics obviously tells us whether something could happen in principle, and kinetics tells us how fast it will go. Yeah, and gives some mechanistic information, which is obviously what we're interested in. But you're only looking at ensembles of molecules, and really we want to get down to what does actually a molecule do, or what does an atom do when it reacts. Okay? We want to really work out things like how fast does a reactive encounter last. What do atoms and molecules actually do during a reaction? This is really where the computer simulations in particular help, because while you can measure certain things, the computer simulations give you the picture behind it often. Yeah? Okay. So really, you could say the starting point for the field was really these sort of developments of these molecular beam experiments. Not that so many people do them anymore, but this is really how you look at a very simple reaction in some sort of detail, and these are sort of cross molecular beams. So you just have two sources crossing, and then you measure as a function of angle what comes out the other side. Yeah? So this is obviously relatively old now, 1986 Nobel Prize work, and you get these sort of beautiful plots. And we don't get such beautiful plots anymore in a lot of ways because these are sort of pre-computer, and these are sort of the typical reactions. And even when you get down to these fundamental reactivity, you get quite interesting quantum behavior coming from the molecules that we want to be able to describe. So these are sort of the three classic, you could say, paradigms in reactive scattering. And this is sort of F plus H2, and K plus I2, O plus I2. And what is it that's different about them? Do you think we've always got a diatomic with an atom? but they all have very different behavior. So if you look at these plots, and it takes a little while as always to interpret what you see in a plot, yeah, so this is scattering. So you're basically getting the things that are colliding and coming off. And so we've got F plus H2 over here reacting. And when they've collided, you get HF plus H. And this zero angle, so as they collide, you've got your HF and the H2 and the F coming in. The zero angle, so over here, this will be if it's going off in the forward direction, and this is coming off in the backward direction. So that's sort of very simply, atom comes in, collides, reacts and comes back. Sort of what you'd expect from a fairly simple reaction. How else is it going to work? The only sort of interesting part here, and this is one, as you can see, rather than it just scattering off in anywhere, you're getting these rings coming off. Yeah, and this is because the molecule is being left in the different vibrational states. So the HF that's formed is in V equals 1, 2, or 3, and so they come off with different velocities as the rest goes into the kinetic energy. Okay. And then if we look at the K plus I2, this is completely different because this is actually the forward direction. So you're getting scattering in the forward direction. Okay, so how is that happening? And there, the sort of the picture, these are very simple pictures, you know, the little potassium comes past this big iodine, and as it comes past, it gets attracted into it and actually reacts on the backside. So the rather than bouncing off and reacting that way, it goes past and it actually extracts the iodine on the forward side and goes out. And then you get the third version, so O plus I2. So again, it's an atom with I2, very different behavior. You can't see it so well on this plot, it's not so nice, but you're actually getting scattering in both forwards and backwards in equal amount. Okay, so what's happening there? And in this case, you get an intermediate form. Yeah, so the oxygen comes in, it sort of gets trapped around the I2, and it will sit in a sort of a resonance state. And so because you've got this sort of long-lived intermediate, you then get, well, it goes off in either direction in equal probability. So you get these different plots. And so the early days of the field were very much trying to understand and calculate these sorts of reactivity. And at the end of the day, so how do we describe this? So this is just very, very simple, the sort of sketch of the theory behind it. Well, obviously in the classical world, motion is described by Newton's laws. Yes, so we just have F equals ma, sort of standard school physics, and we know that we can calculate trajectories. However, of course, you know, in the quantum world, we don't have Newton's laws. We have to solve the Schrodinger equation instead. Yeah, so this is the time-dependent Schrodinger equation. So if we know the wave packet, we know a Hamiltonian, you can work out an evolving wave packet, which is really the thing that we want to solve. So this is the aim of the quantum dynamics simulations. Because if we have the wave packet, we of course can get the probability of finding our particle as a function of time. And then hopefully you can see all of this sort of quantum behavior happening. And then the important thing we then have, what goes into this, is the potential energy surfaces. That's always the thing that you have to start with, because that gives the description of the system effectively. So these are the potential energy surfaces, just going back to the H plus F2, sorry, F plus H2, and H plus F2, sorry, F plus H2. These are the potential energy surfaces in terms of the two bond angles. So we've got the H2 up here, and this is the HF distance. So as our F comes in, this is a transition state, and then this is the channel for the outgoing HF. Okay? And if you look in, just basically following the line, so if you follow this reactive path, you know, if you do calculations, you often do things like trying to find where the reactive channel is, so that we can follow this, the minimum energy path, as we'd call it. You get the minimum energy path. Well, it looks like this. So we have a, you know, the incoming channel, then there's the barrier, and this is the reactive channel going out. And because of this drop, this thing's exothermic, this is the energy that you can then dump into these vibrations. And actually, this is a molecule, this ends up, you know, with chemiluminescence, because you come out in a highly vibrate, well, it's not that high, V equals 3, but it's vibration excited, so it will emit energy. So how do we solve the time-dependent Schrodinger equation? So this is the sort of the first thing that we want to do. It's a sort of a basic thing. This is the sort of what we call the standard method. It doesn't really have a name. You know, it's like in quantum chemistry, when you're calculating orbitals and something, the whole language has grown up. You know, we have Hartree-Fock theory, we have, you know, the various theories. We don't really have this in quantum dynamics, so we just tend to call this the standard method, which is okay. So what are we doing? So we have our wave function, if we know what that is, and you have to start by saying, okay, we have a particular set of initial conditions, and our wave function is actually what we call a wave packet, because it's a non-stationary state, so we refer to that as a wave packet. And contains all the initial, distributions of where your particles may be, and then momentum. Yeah? And then, we know our Hamiltonian, hopefully, because we can work out what the kinetic energy operator is. We've got our potential energy surfaces. We're lucky. So we want to solve this. How do we do this? Well, the standard way of doing it, like in any sort of theory, what do? We take our wave function and we expand it in a basis set. Okay? This is actually, you could say, a bit like sort of Hartree-Fock type ideas. What else are you going to do? But we have a basis set of functions. So for each degree of freedom, each coordinate, each bond length, whatever you've got in your system, depends how you set it up. That defines your kinetic energy operator. You have a different basis set. And these basis sets in general, they can be sort of related to a grid. So we're discretizing our wave function. We are putting our wave function onto a grid. And then you have these expansion coefficients, and this is where the time dependence lies. So these are effectively a grid in each direction. So we have a multidimensional grid, and we have these amplitudes on the grid, and this is our wave function moving forward in time. Okay. And actually, it becomes a mathematically very simple thing that you then have to solve. It is just this equation. Yeah? So we have our initial amplitudes. If we then have this matrix of Hamiltonian elements in our basis functions, you can then solve this to get the time dependence of the derivative, and you recursively sort of do this and propagate the wave function forward in time. It's actually quite simple to do. But, yeah. Okay. However, you have one big problem, and that's the fact that it is very, very computationally intensive. No? And you can see that simply by looking at these number of expansion coefficients, so these amplitudes, because we've got this direct product basis set. So we've got, if we've got 100 basis functions for each degree of freedom, and you've got 3 degrees of freedom, I've got 100 to the power 3 coefficients. So it goes up exponentially. 4 degrees of freedom, 100 to the power 4, 5 to 100 to the power 5. So it gets very big very quickly. And this was the early big bottleneck that you couldn't get past. But you can do atom-diatom types, so 3 degrees of freedom. You can do those sides. You can do them very accurately, very simply, and you get a very nice sort of picture out of it. We'll come on in a bit as to how we try and get past being able to do atom-diatom. And this is the sort of picture that you then get. So for people who haven't seen sort of wave packet dynamics, this is for the reaction H plus H2, potentially not the most exciting chemical reaction, but it's one of the ones that the theoreticians, the quantum dynamics people, can sort of claim that they can do it more accurately than the experimentalists, because you can really do everything at a real high accuracy, and you can calculate the reaction, the reactive cross section, state to state specific, and so on, and actually, a very good accuracy, because it's quite a simple system. But anyway, so we set up our system. There we are. There's the atom going to come down and interact with the diatom. We have the potential energy surfaces, and you sort of get a picture. You get pictures like this. So this is the wave packet as it comes in. This is just the sort of, you can imagine you've got this. It's like a Gaussian function, so it's a blob coming in down the reactive channel here, and this is as it goes over the transition barrier. So part of it has reacted, and part of it is reflected. Yeah, and you then can extract from that all the information about the reactivity. Okay. So this means we then have a basic recipe for doing what we call wave packet dynamics or quantum dynamics, and that is, well, we have to calculate the potential surfaces. We then, of course, need an algorithm to propagate the wave packets, because while this is a mathematically fairly simple equation, as I showed before, you've still got to actually have some way of doing it, which is not so straightforward, but I'm not going to go into that particularly. And then, but once you've done that, you calculate the flux into the channels, and you can calculate, in principle, everything you need to know. And you then get these plots. You actually can see, even for this very simple looking reaction, so this is looking at the reaction probability as a function of the incoming energy of the H, and it's not something straightforward. You imagine sort of, if you think sort of simplistically, it's just going to depend on how much energy you've got. Yeah? The more energy you've got, the more likely it is to react. So obviously, you need to have enough. This is what we sort of learn as undergraduates in chemistry. If you've got enough energy to react, there's a threshold, then it will react. But you actually find that this is just for the collinear. So you've got H and H coming in. It's a very structured thing. So you have, this is the initial threshold, but then you get certain sort of regions, you get no reactivity happening. And then you get these sort of different resonances and all sorts of interesting things happen. And this is purely from the quantum structure of the interchange of the energy between the kinetic and the vibrational and so on. But this is the sort of information you can pull out. So this is just looking at plots for different starting states. So it's V equals 0 to ending in V equals 0, V equals 1 to V equals 1, and so on. And you can really, let's say H plus H2, I think has been pretty much finished, unless someone wants to do some more. Okay, so that's the sort of, you could say, the simplistic thing. We're still not able to really see what's happening in the reaction. This is, you can use the simulations and you can pull out much of it, but is it possible, and this is where almost the connection to the experiments come in, to actually watch a reaction? You know, can we do something like freeze frame photography? So this is one of these sort of typical pictures that we can bring up. So this was the first credited freeze frame photography. So this was to settle a bet in 1878. Does a racehorse at any point have all four legs in the air? Which was apparently an important question to answer. Well, it was in the sense that a couple of very rich people had bet a lot of money on it. So that's probably not that. And it was that the answer then solved by this character over here, Edward Muybridge, who was one of those slightly English eccentrics. It actually happened in America, but he decided to spell his name this way because it was an Anglo-Saxon spelling. Anyway, so it's, and he developed this scheme whereby on a racetrack, he set up a load of cameras in 1878, so not particularly sophisticated cameras, with strings going across the track. And as the horse went past, it triggered each of the cameras in turn. And this gives us this sort of freeze frame photography. And he managed to capture the horse. And there you go, end of story, bet finished. And that was the first sort of freeze frame photography. He then actually spent most of the rest of his life, if you look him up, taking pictures of naked people walking around. Because all in the name of science, of course. Yeah. Yeah. But anyway, horses are a bit big. They're relatively easy to track, but we need something a little finer than that to capture molecules. And this is where the whole field developed using lasers, because lasers are obviously, you know, the sort of tool that we can use for this. And this is the field, well, it's got sort of various names these days, but transient absorption spectroscopy or femtochemistry. So what sort of time scale have we got to go down to? Well, we're not looking at a horse. And the answer is, well, vibrational motion in a molecule, you know, these are the order of femtoseconds. This is why it's called femtochemistry. We've got to get things down to the femto region. And these days, if you want to watch electrons, you go down to the atto region. This is 10 to the minus 15 seconds. You know, this is where, and these days you can actually get down to even 10 to the minus 18-ish, or get in that direction to watch the electronic motion rather than just the nuclear motion, but I'm not going to talk about that today. So instead of that, what's done is, following the work, this is all the sort of, you could say, pioneered by Ahmed Savile. This is the sort of the basic pump probe scheme, which we use for sort of femtochemistry type experiments. And the idea, it's a similar thing. It's, in a way, it's like the racehorse triggering strings. So you start the reaction, you have a short laser pulse. These can be, you know, of the order of 100 femtoseconds or less. Yeah, so that comes in, and we have our molecular beam. So we've prepared the sample in as well as we can. I'm not doing this. The people who do the experiments can. In some sort of well-defined initial state, the laser pulse comes through, excites the molecules. So they're coherently excited at one point in space, one point in time, in the same way. And then a second probe laser comes through, and there's a time delay between these two. So the probe laser comes in, we get a second signal, and that tells us about where the reaction has got. Okay. And so by repeating this with many different time delays, you build up the snapshots. So you have, so you can sort of build up the same idea of a little movie, a molecular movie. And all of the schemes, I think, since that really are based on this scheme still, and the differences are things like how you actually get the probe signal, what do you get out of it, how do you find it, and so on. And that's where all the clever optics come in. Yeah. Fortunately, as a theoretician, we don't have to worry about that. We leave for people to measure these things, and we just have to do the calculation to understand. Because one of the problems is these signals can have a lot of information in them, but they're actually really quite sort of complicated, and everything overlaps everything, and often needs calculations to support it. So this brings us into the sort of the realm of photophysics and photochemistry. And this means, because we're working in excited states, we obviously excite a molecule and then watch it evolving in time. Okay, so we do sort of divide things into these two classifications. Photophysics, is a fairly static thing. This is just about what happens to the molecule or the different possible pathways for the energy flow. So we have this Jablonski diagram is the sort of typical picture. And these are our energy levels for the molecule. So we'd sort of say, as a chemist, would say this is very much the sort of the physicist view of a molecule. They're just sort of lines, with sort of energy levels there. And so we have our molecule sitting in the ground state, can absorb a photon, you get relaxation. You can change between states of the same spin with internal conversion. You can change between states with different spin, intersystem crossing, and we can have fluorescence and phosphorescence and so on. So that all these processes compete with each other. And then photochemistry is put on top of that when we now bring back in the potential energy surface description, and we look at our wave packet evolving over a potential energy surface and going to different products. That's the sort of the photochemistry part. So this is what this rather strange looking potential energy surface is showing. So we start down. Oh, there it is. Lost it. So here's our initial wave packet. We excite it up to here. It moves around. You can end up in a non-reactive minimum, but of sort of, you could say, particular interest in the sort of fundamental fast photochemistry area is these sorts of regions where potential energy surfaces get close together, where you have things that are called conical intersections. And this is an example of it, because what happens is if you have one of these regions in potential surfaces, and they are actually common, it's not as to whether they're there, it's as to whether they're accessible, rather than fluorescing, because if we end up here in a non-reactive minimum, you will fluoresce, you've got to give off light to get back to the ground state, whereas here you can get back to the ground state by passing through one of these intersections, getting back to the ground state, and then you've got to dissipate the energy, but you go on then on the ground state to form the different structures. And a lot of the sort of discussions that go on are, well, you get photo products, are they formed on which state? Excited state, ground state, does it, and so on. These are important things, and they have, I will show sort of some quite interesting properties that it takes a little bit of working out. Okay. So Surveil, a bit like in the scattering, there are sort of few classic experiments that sort of show the ideas. Yeah. So this is looking at just a vibration. You can sort of see the sketch. This is I2. We're doing an excitation. Because we've excited the molecule, it's not in an eigenstate, so it will start vibrating. Yeah, so the wave packet will start to move backwards and forwards in the well excited state. And then with the propulse, when it's here, you get signal. When it's here, you don't get signal. So you get this sort of signal that will be matching to the time scale of that vibration. Or if you look at ICM, this is just a dissociative reaction. So you just excite, molecule dissociates, but again, you could track it as it goes down that dissociative curve and you can work out how fast. What does it mean for a bond to break? So this was really answering the question, how long does it take for a bond? How far has it moved? Yeah. And the answer is actually, the bond breaks not just quite fast in whatever it was, 100 femtoseconds or so, but it hasn't moved very far. It doesn't actually move very far until it's lost the character of the bond. It's only about an angstrom. And then the more interesting one, this is the one in the sodium iodide. This will be a lot of what I will then come on to in a moment, is sodium iodide is interesting because, you know, one of the classic things as a chemist, well, we know that sodium iodide, like all the alkali halides, when it's bound, it's an ionic. Yeah, so you've got Na plus by minus. Whereas when it dissociates, it comes out as atoms, sodium and iodine. But if you follow the two states, you get Na plus I is the higher energy, and that potential energy curve crosses the one of the atomic curve. And this is then one of these crossing regions. Okay, we've only got one dimension, so it's not a conical intersection, it's an avoided crossing, but they're just sort of shades of the same thing. And actually what you see then is, interestingly, when you do the pump-probe experiment, you get sodium. So if you just watch the formation of sodium, that's i.e. how much comes out over here, if you just watch that, it gets formed in this sort of stepwise manner. So as the wave packet comes across, each time it comes to this crossing region, you have a probability of it dissociating, a small amount comes out, and the rest just vibrates back. So you're actually watching this sort of probabilistic, it's a quantum process because part of it goes one way, part of it goes another way. And we refer to this as the bifurcation, the wave packet. Okay, so how do we describe photoexcitation? It's the same as I was talking earlier about the scattering on a potential energy surface, but now we've got many of them and they're coupled, right? Just adds the extra complication. And we have two pictures that we use to do this. So one is the standard, what we call the adiabatic picture. So here we have the potential energy surfaces that you can calculate with quantum chemistry. They're energy ordered. These are the eigen states that come from the electronic Schrödinger equation, but they also have couplings between them. And the coupling comes from what's called non-adiabatic coupling. So these crossing regions are called non-adiabatic regions. And this is because the adiabatic picture breaks down of these regions. So this is how so the basis of this is, if this F term here was 0, we have the Born-Oppenheimer approximation. So that you have your nuclei just move nicely over potential energy sequences. However, this F, these non-adiabatic couplings, are due to the fact that the electronic wave function does depend on the nuclear positions. Born-Oppenheimer approximation is the fact that the electrons follow the nuclei exactly. And so we have to actually consider these terms, which in general can be thought of as being small, because there's actually a nuclear mass term comes into that. But you can actually write them in this form as well. So you get a 1 over delta E. And so when the electronic surfaces become close, or worse, to the conical intersection degenerate, this term becomes large or even singular, which you get surfaces that look like this. Here we've got a conical intersection between them, which is okay, fair enough. It basically adds an extra momentum term to everything and a coupling between the states. This allows us to move like that sodium iodide as it gets to the intersection region. Part of it's on one state and part of it's on the other. However, this brings problems for simulations because singularities in general are difficult to treat. You get an infinity coming in. So instead, we want to work in what's called the diabatic picture. So we have to transform between these two. I'm not going to go into how we do that. But in principle, you can transform. In principle, you can approximately transform between the two. Oh God, obviously we haven't done it. Okay, good. No.
Twice, just do it twice.
Okay. So we have the diabatic picture, and here we now have potential surfaces that look like this. So they sort of cross through each other, and the couplings are seen there as potential like terms, and these are much easier to deal with. The problem is, how do you get them in the first place, which is a whole field for itself. If it wasn't for this, the whole thing would be quite easy, actually. Okay. And conical intersections, they have signatures that you see actually when you look, these are just sort of typical things. How do you see them? How do we know they're actually important? Well, you get things like this. These are old plots now. Octatetrene, isomerization. There's a certain part you get radiation, and then all of a sudden, when you excite, or this is actually a temperature dependence, as you go to higher energy temperature, suddenly the radiation no longer radiates. So you're reaching a conical intersection, you're getting radiations to decay to the ground state, or alternatively, this is this classic example of pyrazine. We have this broad band for the S2, a well-structured S1 band in the spectrum, and that's because there's actually a conical intersection between these two states. So this is a very short-lived excited state. Everything you excite just comes quickly to the S1, which is long enough to have structure. Okay, so how do we sort of simulate this stuff? So it's the same as before, but with just the extension that we have to have the extra states. And so a simple example of simulations, we now have our extended Schrödinger equation, which is now a matrix, so we have all the couplings in them as well. And a simple calculation, this is the sort of scheme that we think of. We have our initial wave packet, that's the ground state one. We excite it, it moves around in this manifold of excited states. We have the crossings, etc., etc. And you can do things like calculate the autocorrelation function. So just the wave function overlapping with the initial one. Fourier transforms that gives us the spectrum. However, we of course want to do things with more than 3 degrees of freedom because that's actually not that exciting. And as I say, the standard method scales really very badly. It scales, we talk about this is the curse of dimensionality or the exponential scaling of quantum dynamics methods. And that's just due to the fact that you have this exponential scaling of the number of expansion coefficients. So this is where our sort of developments of different methods come in. And one of the basic sort of, you could say, first step up from just doing the standard method is to use the multi-configurational time-dependent Hartree method, which is what I was involved in developing when I was in Heidelberg. So the wave function form looks much the same, this initial ansatz. The only difference is that we now have time-dependent basis functions rather than time-independent. which we again actually describe further in the grid. So this is all a big contraction scheme. And you can actually do very large wave functions this way. So with the latest sort of versions of this, you can actually treat wave functions with, well, up to about 1,000 degrees of freedom in various ways. So you can do big wave functions. That's not a problem. Propagate them very nicely. You then just have the problem, I need a potential energy surface, but we'll come back to that. Because, yeah, what do I do for a potential? If you're doing a small system, how do you get a potential energy surface? You just calculate many, many points. Yeah? And you have to, you say you've got a three-dimensional system, you can calculate whatever, 100 points in each direction, that's 1,000 points. Yeah, you can do that at a relatively high accuracy. You can fit a function to it, you get a potential energy surface, you can do your calculation. Whereas if I'm looking at some molecule that has 100 degrees of freedom, you're not going to do that. And especially because excited states, quantum chemistry calculations are really not very accurate. So you would spend a lot of time not really getting anywhere. So what we do instead is we tend to use model problems. We do reduced dimensionality problems. You extract the important degrees of freedom. So we have to play all of these sorts of tricks to be able to do sensible calculations. And quite a very useful model that we use a lot is something called the vibronic coupling model. So all we do here is we take our Hamiltonian, so there we are, we assume we're in a diabatic form. So we get around this problem of getting an adiabatic diabatic transformation, and we just say, well, okay, we've got a set of potentials, and we do Taylor expansions. And this fits the surfaces very well around the Frank common point. So just around that initial point of excitation, so you get all the initial fast dynamics quite well described. And this is a method that, as an example, this is just the sort of things that we can do with this. So this was an example of study on this malleimide. So malleimide is a fluorophore. It can be tuned. So this is from a little project with Rachel O'Reilly in Birmingham. You can tune these things by putting on different groups. You can basically get any color you like. Yeah, these are used in sort of imaging experiments. But how do they sort of work and so on? So they even show sort of some quite interesting properties. So this was actually worked partly with Sandra Gomez in Salamanca. And this just shows the example of the ideas of what we can do with these linear vibronic coupling models. So you take your quantum chemistry. I've just gone something sort of. Oh dear, I've gone sort of moved. Press too much.
Press too much.
Yeah, press too much in. Right. So you calculate, use quantum chemistry, you calculate points, but we don't have to have quite so many as before, because you're really only interested in sort of parts of the surfaces. You firstly have to obviously work out what level of theory you're using. So this is CAS-PT2, which you can't do for everything. So you use EOMC-CST, but you have to benchmark it. You get the points, and then you fit the model to it. And then you can run the quantum dynamics calculations. Really all you need to say. And then you can get, so this is the sort of example of the quality of the spectra that you can get out. So this is, you do just in the same way as I sort of said before, same scheme, excitation, propagate the wave packet. But we've now got, I forget how many degrees of freedom we got sort of 24 degrees of freedom rather than 3 or 4. And you can calculate, so if we excite the S3 state, so there's really the two states that are bright, yeah. So these two states are bright, the S3 and the S4, and the S1 and the S2, they're actually dark, so you can't access those directly. And if you excite to S3, well, this is the experimental spectrum, yeah? And this is our calculated spectrum, which I think agrees really quite well. You can get the sort of the little bits of sort of structure up on the rising edge. Yeah? But this is including all the 24 modes. And this is, again, excitation to S4, and this is our calculated spectrum. So you can actually, you get, and as a result of that, you can actually assign what all these lines are. So one of the interesting things with malleimide is, and it's unusual, is that actually S4 has a well-structured spectrum and S3 doesn't. Usually you expect if you excite to one of the higher states, there's little structure there because the thing relaxes so fast down to S1 before it fluoresces, something called Cash's rule, returns to the ground state, it just tends to be a fairly broad blob. And the reason for that is purely because, well, you can see S4 is actually quite well isolated. Yeah? So you can actually be in this state and it lives around for a long time. So these molecules actually can show what's called dual fluorescence as well. Yeah, yeah. Whereas S3, you come into S3, you can sort of see from the potential surfaces, if you're here, it crosses with these lower lying states, and so the energy flows down very quickly. Yeah. And you can sort of see that in the the population. So this would be the sort of lifetimes that you could potentially measure if you did the experiment. So excitation to S3, you get very fast population loss. Crossing down, the yellow line is actually going into the S2 state with some structure. Whereas to S4, it's relatively, it's a fairly slow decay, just sort of just decays down. Right, so how do we go past that? Because that's all well and good, but we're still fairly struggling to do long time dynamics. We can do large scale on this. You can actually go to say 30, 40, 50 degrees of freedom. You can calculate the spectrum one. Not too difficult. As long as your electronic structure is good and so on. But how do we go further? Because as I said, we are at the moment only describing the potential energy surface around the Frank common point, so around where the initial excitation happens. Well, most photochemistry takes place longer timescales and away from that. Yeah, and we actually know from a number of our calculations that we miss features, ring openings, these sort of even just sort of any isomerization is impossible to describe. Well, it's not impossible, but very difficult to describe with these simple models. So as I say, how do we go past that? So real photochemistry needs flexible molecules with long times. And the sort of, whether it is the final solution, we'll see, but we're moving towards our solution here, we are doing what's called direct dynamics. So we said you can't calculate a potential energy surface from the start because it's just too much effort. You would get through many PhDs until you got anywhere. Not a good idea. These fitted models, they're great, but they're limited in their way. So let's see if we can calculate the potentials just where we need it, where the wave packet goes. And this is direct dynamics, what we call on-the-fly potentials. So how do we do that? You can't use the standard schemes or even MCTDH with on-the-fly. So on-the-fly means that, as I say, you calculate the potential surfaces as the wave packet moves. You can't use those grid-based methods because by definition, you have to know the potential energy surfaces in advance. So we need something else. So instead of that, we are using what are called Gaussian wave packet methods. So if we take our wave function and we expand it in a set of Gaussian wave packets, everyone knows what a Gaussian function is. It's just a bell curve, this sort of e to the minus x squared. But these are fairly localized. So the Gaussian function has a center. And in fact, you can sort of say it has a center and even a central momentum. So it sort of has a point at the center that you can follow. And you only need to know the potential surfaces around this center. So this gives us a scheme that allows us to, well, we need to know the potential around the centers of these Gaussians, which we can calculate using quantum chemistry as they move. So we're able to set up our wave function with these basis functions and propagate them and calculate the potentials on the fly. Okay, so we've done quite a lot of work on this over the years because unfortunately these Gaussian functions are not well behaved for various reasons, but I don't need to go into at the moment. But the answer is, so just as an example of the sorts of things we can do. So this is one of our early studies that sort of work quite well. This is just looking at formaldehyde. And this was one of those examples we said, okay, formaldehyde, this is something small. Surely we can do this very easily. It's only got 6 atoms. So, however, it's not quite that straightforward, actually. It's actually a very interesting little molecule, even though it's this small, because in a way, you can claim when you look at this, this is the start of life and everything, because it is meant to be one of the space precursors for DNA bases and so on. So you can do the whole, whatever, very important. However, things with nitrogen are actually quite difficult. The quantum chemistry is quite horrible. This is sort of the sort of example. So the student who did this, Erin, spent quite a lot of time trying to work out. You do different. Anyone who has tried to do CAS-SDF calculations would understand this and the pain involved with trying to work out different active spaces, different state averaging, and the whole thing. The states move around. And anyway, after a while, we decided on what we were doing. But you had to actually include. We're only really interested in the lower few states, but you actually had to include about 8 states in the whole thing because of the way it works. Relatively cheap 631G star CAS-SDF calculations, but anyway, that's the way it goes. And then you can, but when you've got that, you can just run the dynamics and the surfaces come out. So these are sort of cuts through the potential surfaces, and this is looking along the NH2 symmetric stretch and along the NH2 anti-symmetric stretch. And they're looking a bit, we're a bit better now, but you can sort of see they're wobbly, but you've got this sort of diabatic curves, they're crossing nicely, so they're behaving as they should. You just get these things, unfortunately, it's a typical result of CAS calculations. Your CAS sort of breaks down because there's clearly some other states that you're going to want to. But anyway, you get some sort of reasonable surfaces, and you can then plot the populations as before. So this is after excitation to S1, slow decay, to S2, fast decay, as we'd expect, and the S2 cascades down through the state. So it sort of was working quite nicely. And we also have the advantage that because you have this flexibility with these Gaussians and the trajectories of the centers of the Gaussians, you can actually, you don't have to say in advance where your reaction channels are. So you can see, well, how does the molecule actually react? And it turns out that this molecule had, even in our sort of fairly simple calculations, there are a number of different ways that it falls apart or not. So this is after excitation to S1, and there's a whole load of reaction channels. Basically, these protons fall off, the bond breaks in the middle, etc., etc. But the protons always come off out of plane. Yeah, that was the sort of the thing that I think was quite interesting. Always, it was out of plane. So it starts to sort of, you could say, vibrate, and then the protons will come off out of plane. Whereas excitation to S2, there's really only one dominant reaction channel. That's this purple line here. It decays off because of the way that the calculations are done. You absorb the thing coming off, and this is in plane. So the H just excitation, proton comes off. So you can just see these without having to say in advance where your channels are, which is rather nice. So just a sort of a final couple of examples on this. There is other ways of doing these direct dynamics calculations. A typical sort of reaction way that these are done by most people, because they're much simpler, is something using trajectory surface hopping. So here we set up classical trajectories, propagate them as a sort of the wave packet moving over the surfaces, and then use a probabilistic, because obviously you've got to work out how to describe the things over the different surfaces. So we have this probabilistic term that as you approach a non-adiabatic region, you will hop between the surfaces and sort of be able to calculate the crossing between them. And it's really a very simple, it has great scaling. We're just doing classical trajectories. And again, you can do this direct dynamics because you're just doing a trajectory, you have a point you're following, you can calculate forces and energies using quantum chemistry. So there are a lot of people now who are using these sorts of methods. But the question is, you still have, here you have classical nuclei. We don't, we have quantum nuclei. So how important is that? And so this was sort of one example. So we actually now have the rather nice thing, and this is thanks to the work partly from Christina, because she's been involved in this, is we could do surface hopping and our sort of wave packet dynamics all in one code. So we can do it on the same potential surfaces. And as an example, this was a little study looking at a fairly classic sort of ring opening. This is cyclohexadiene going to hexatriene. It's quite a complicated photochemistry because there are 3 states involved. So there's this sort of a crossing through here. Organic chemists call this, I think it's the, I can't remember, the Lug-Oesterhoff model of photochemistry, where you get this particular crossing between this biradical and this sort of singlet state. But you want to model this, huh? And so, you know, we could do this and both with the surface hopping, so starting in the initial state here, because you've got to cross from this state to the red state before you get down to the blue state. So you follow the trajectories, and this was our VMCG calculation. Although, and this is the surface hopping. The one thing we can't yet compare directly, it's one of our problems, is because we are working in the diabatic picture, the surface hopping is in the adiabatic picture. So they're actually a bit different. And yes, we can transform, but we can only do this. These are our VMCG adiabatic populations, but they're only approximate because we can't do the transformation exactly. They don't compare. Well, they compare. You've got similar timescales, and you've got, yes, the 3 states involved, but the details are actually a little bit different. So I know we're trying to work out where the differences come in. But certainly one of the differences is if you do surface hopping calculations in the way that they're usually done, you will calculate your quantum chemistry at each time step. So say every half a femtosecond. These are being done for 150 femtoseconds. You're going to need a few hundred trajectories. So you do many, many calculations. Oh yeah, about 200 trajectories, so this would result in 60,000 quantum chemistry calculations, a lot. What we do instead is we're actually calculating at points, we build up a database of structures and we can interpolate through them to get the surfaces. And so we only needed to do about 1900 structures for this, so that's actually a lot of saving of time, which is rather good. So that's one of the things we're working on. When each calculation takes 3 hours, you don't want to do 60,000 calculations, it's a lot of effort. So there's yeah, so I've just got one or two little examples. So this is something because, hey, you've got to put in the pretty sort of pictures at the moment. There's this green fluorescent protein that's responsible for jellyfish glowing green, that's used in a lot of sort of imaging experiments these days. Huh? And so this is the protein that's inside, and there's a little chromophore in the middle, which sort of it is activated and glows this bright green color. So this is actually the chromophore, HBDI, and it's really quite an interesting little molecule. So it actually forms spontaneously from inside the protein. There's a serine and a proline that sort of just spontaneously form this thing. So it's not like a chromophore that comes from outside, it's formed in the protein. And the activation involves a proton wire. Yeah? So to activate it, this phenol side has to lose a proton to this water. The water has to pass a proton onto this. This is a threonine residue on the protein that then loses the proton around its glutamate. Yeah? And this is one of the things. So in the sort of the biology field, there's a lot of discussion, what's the importance of tunneling or not? Is all of these proton transfer mechanisms, which are often the sort of time, it's the step that limits everything. Is it that you have to get the protein to be in the right conformation, or is it due to tunneling? Very difficult question to answer, but there have been studies on this system, both using QMMM and classical dynamics, that show that you can do this proton transfer wire with the protein getting to some conformation. It's a relatively complicated process. To date, there have only been quantum dynamic simulations on really simplified versions of this chain, which show that yes, you can do it with tunneling, but they were so crude, you could say, that they were getting a tunneling time or a transfer time along this chain of the order of 100 femtoseconds, whereas it's been measured to be about 2 picoseconds. So they're clearly sort of not that realistic. So anyway, so we thought we'd try this with our direct dynamics. So we set up this thing's what's called a cluster model. This is the taken from the protein, and we've got our little chain. And then we'd say, well, we can't still, well, to make it a bit easier, this is 48 atoms, there's a lot of vibrations. Which are the important vibrational modes? And so the person doing this, Susanna, pulls out which are the important modes. So where do the forces go that are initially activated, and where's that coupling into? So we only included those. Right? And so what was really interesting, or it was for us, at least, was you just do this, you run these, it's only on a single surface, there's no conical intersections involved, just doing this at the TD-DFT level. And what you see is that, well, nothing happens for quite a long time, about a picosecond, and then at some point, this one vibrational mode actually starts to get activated. Huh? And then at a later time, these other two start to get activated. And you can actually then, sorry, not too fast, and you can relate that then to a percent of proton transfer. And the proton transfer actually happens on this mode 116. These are the vibrational modes. Huh? And that one is actually this one. See, I, as a sort of physical chemist, had naively thought you'd excite the chromophore, the excitation goes onto this ring, and therefore it would be a push. But actually what happens is you firstly get this transfer, followed by this transfer, followed by that transfer. But I was told by a biochemist this is obvious because these are photobases. But okay, fine. But this is sort of but in any case, it's about the right time scale, yeah, and you get this happening. So this is the first proton transfer happening, and then this is the second one starting to come through. And interestingly, if we do the same thing, but just using classical trajectories rather than our coupled quantum Gaussians, you get nothing. Over 2 picoseconds, starting with exactly the same conditions, we don't see anything. So that means that in this admittedly simplified model, we don't have the protein environment. You can get proton transfer via tunneling, because it's a tunneling process, yeah, through the barrier at the end. So probably, as always, the environment and the tunneling's involved. So yeah, the way it goes. Okay. And yeah, so that was really, I think, all I wanted to go through. So basically, as a summary, what are we trying to do in quantum dynamics? We're trying to understand these sort of fundamental things that are going on in small, medium, large scale molecules, whatever, at different length scales and different time scales, but it's always the same thing. When are the quantum effects important? If they are, and they typically are if you've got tunneling involved, so light atoms, which are quite important everywhere, potentially even if it's just some sort of rotational and translational interplay of motion, you get resonance states involved. Certainly if you have conical intersections involved, you have a massively quantum process, and then you have to sort of resort to these methods for accurate simulations. And at the moment, I'd say we're at the stage now we can do quite accurately small molecules if you can get potential surfaces. And we could do in an approximate way, but including a lot of the quantum details now with these direct dynamics methods. But we have two big bottlenecks still. One is the level of electronic structure theory, because really for excited states, there is no good electronic structure method that is able to describe things over a range of configurations in a stable and easy to use way. It's a big problem. And then, yeah, we can improve on the efficiency, but we're certainly getting there. Okay, so with that, I'm just sort of, there have been many people involved in the work that we're talking about. Obviously, my sort of main collaborators on a lot of the work with the development of the MCCDH method and the VMCG and so on. And then just had to put this up while I'm here in Madrid. And tomorrow I'm going to go to Salamanca, so we have to put up people who are working on the project there. And the work was presented so from Andreas Lehr and Sandra, that was the Malamide work, and Jamie Kujabaharry, that was the CHD HD, and Erin did the formamide, and Susanna the GFP work. So with that, thank you.
Thank you, Graham. So now it's time for discussion. Fernando, please.
Very nice talk. I have, since you are the expert in this nuclear dynamics, I'd like to know your opinion about the method, this is direct dynamics that you have presented, how close it is or how different it is from multiple spawning methods. Advantages, disadvantages. In principle, as far as I know, multiple spawning methods also they describe the nuclear motion by using Gaussian functions on potential energy surfaces. So could you? I'd like to know your opinion.
Okay, no, so you're right. They have the same sort of basis. I just put up the where is it? Yeah. So multiple spawning has the same. That's yeah. So it describes the wave function in principle completely because it's a complete description. The difference between our method and multiple spawning is multiple spawning, the Gaussian functions follow classical trajectories, whereas our method, the Gaussian functions, the trajectories they follow, they're coupled, so they're actually quantum trajectories. This means multiple spawning, if you get a barrier, it won't describe tunneling droplets. And this method does. And the other main difference is the convergence. So multiple spawning, the nice thing about it is you can start with a small basis set and then it spawns, so it knows when to add functions, which is great. It starts with a minimal basis set and grows. But because they follow classical trajectories, you might need hundreds. And this is a lack of variational basis in that sense. So you don't know how many you need. And I've actually sort of had, with some examples, our Gaussian functions, you can get them to follow classical trajectories rather than the quantum trajectories. You need a lot more of them, many more. So we converge faster, because they talk to each other. Spawning is much easier to implement as a result and quicker, but you need more functions, which I actually think in direct dynamics, the fewer functions you need must be an advantage, because when all your effort's going into a 3-hour calculation on a point, if you've only got to calculate, 60 trajectories rather than 400. Yeah. Thank you.
It's quite impressive to see how large systems you can treat now. I was wondering the comparison between quantum dynamics and trajectory surface hopping. I think the idea of using a database can also be applied to the surface hopping.
Absolutely. You can, and in fact, the calculations that are showed here with the surface hopping, when I say they're on the same surface that they are, because they're both. So how you do this is, or how we're doing it now, is you run the direct dynamics. You collect your surface. You actually have to do it repeatedly until you've got enough points, and then you can run the calculations on your, so you don't keep generating more points. And then yes, you run the surface hopping on the same surfaces, which I think is why we can say this is a genuine comparison, because these are surface hopping calculations and the VSG on the same surfaces. We're not, because you always have this problem if you're doing direct dynamics. You've got the random sampling, you're generating different surfaces each time. So yes, you can do that. Yeah.
So my question about this slide is actually, do you see from the chemical point of view if there is a difference in the outcome? Because what you show here is the population, but is there like a different reaction or different outcome?
We didn't really analyze that in any detail. I don't think so here, because it's all coming down to the same region. It's just as to how much comes down. We do see it in some, maybe. We're still early days on this, but this is one of the things we want to test. Do you? And I think there are some situations that surface hopping will struggle with, it actually does remarkably well. I'm actually impressed with what it can. One of them is when you have multiple crossings, yeah, because surface hopping, because it doesn't describe the nuclear coherence properly, because you have classical nuclei. Of course, when you go through a crossing point, you've lost that coherence, so you actually are not moving in quite the right way. So if you hit a second intersection, yeah, so this is what we're looking at a bit at the moment. How well can you describe these things?
So maybe if you want to test the chemistry, that there is a test from Federico Agostini, quite gross about who doing exact factorization.
Mhm.
So they checked like a 3-membered ring, which can break in different ways.
Yes, yeah, yeah.
And that's-
Actually, that would be a good test. Actually, we should try that one. Yeah, you're right. That would be a nice test. We're actually at the moment just finishing off some tests, which we're looking at. So Basil Kirkhope likewise set up these 3 tests. Oh, God. It's that one on the side. You have this one on the side. This is.
I forgot to warn you about the side.
Which likewise, so that's Ethan, DMABN, and full beam. We're starting, yeah. So you're right. So Federico's that big one. Yeah.
That was maybe, I hope it's not too technical, but when you do this exploration of the potential energy surface and then the interpolation, like you have some method to decide, like, do I actually need to calculate the next point or not? I suppose that is done automatically.
Yes.
And that is probably pretty not, equity method is not so easy. I mean, like, how?
At the moment, we do it in a rather crude way, so it's just when the molecule has changed by a certain amount, and we just do it by, if it's changed by, at the moment, I think the usual criteria we can change it is 0.2 Bohr, then it will calculate a new point. So it's big. There are better methods, there are statistical methods. I actually think that one of the ways, so there was a lot of stuff that was done, there was work from Mick Collins in Australia on GROW, they GROW procedure, quite a long time ago, which Terry Franklin took on. Which no one seems to be doing much. And that was basically to build up surfaces. And they built up a lot of statistical analysis as to when you're doing these things, where you should put viewpoints or not. The way the interpolation is done is with a Shepherd interpolation. So it's you need Hess first order, second order, and so on. And then you basically take averaging, you're doing weighted averages, which again, you can use to tell you where your surfaces are good or bad.
Yeah.
But we haven't got that far yet. But yeah, because that would be, yeah.
But thank you.
So I'm curious about the formamide results you showed.
Mhm.
So you mentioned that, well, you see the bond breaking, all these normal things, I would say. Do you see any evidence of hydrogen migration?
We had one of the many did do one hydrogen migration, because for some reason I don't remember. I've done something again on this. I can't remember. Yeah, so there's that, because the hydrogen migration going from the amide to the acid is the interesting pathway. There was one, so we got a very, very small amount of it.
Yeah. I guess it's very small.
Yes, I don't know what it's done to you.
No, but it's not even working.
I've frozen everything, have I?
Okay.
Yeah, so there was one of the sort of about 60 Gaussians that did do that when you excited to S2. Yeah.
Oh, yeah.
Okay, there we go. See if I get back to, this one. Yeah, so it's the proton coming across here, which is going to again,
Like really small, but you do see.
it is on, however, it must be considered, these are CAS SEX surfaces, which are actually, the energetics are not great. We wanted to redo these at some point at CAS PT2 or something, because then the surfaces will get closer. We might see some different things. Yeah.
Thank you.
But if there's no more questions, let's thank again, Graham.